Hello, everyone. I'm Guillermo Varela from Magnet Europe, and I'm here today with Oriol de Quintana and Miquel Baliño from Saitec Offshore Technologies. Oriol is a civil engineering with a specialization in maritime and offshore structures, and Miquel is a BIM modeler with experience in large-scale projects within the industry and energy sectors. Today, they will show us how Rhino is integrated in their workflow during the design process of a floating offshore wind platform with a parametric script they have developed using RhinoScript and also the 3D model of the platform. Remember that in the last 15 minutes of this webinar, we will have some time for Q&A, so you can ask questions in the chat and we will check them at the end. Also, I would like to mention that the webinar is being recorded and will be available on our YouTube channel where you can find more webinars and tutorials. I would like to thank Oriol, Miquel, and their team for presenting this webinar, and that's all from my side. So you can start with the presentation if you're ready.
Okay, so thank you very much, Guillermo, for the presentation, and also thank you everyone for joining this webinar. So I'll start by sharing my screen. Okay, so first I would like to show you what Miquel and I are going to cover today. So first I'll briefly present what is Saitec and Saitec Offshore and what we basically do. Then I'll describe a little bit the SATH technology and the DemoSATH project, which you can see now on your screen. And then we'll enter to the topic of today's webinar and see how Rhino is integrated in our design workflow. And following that, I will present the in-house parametric script that we've developed, showing a couple of demos. And then Miquel is going to jump in and talk about the modeling process and display the 3D model of DemoSATH. And later he's going to talk about rendering and interoperability. So about Saitec. Saitec is a civil engineering company which has more than 30 years of experience in different sectors such as roads, railways, water, energy, etc. So Saitec is based in Leioa, a city close to Bilbao in the Basque Country, but it also has presence in other countries. Then Saitec has always been involved in R&D projects, and a little bit as a result of that, Saitec Offshore Technologies was created in 2016 as a spin-off from Saitec, with the main intention of developing an innovative and competitive concrete floating technology for supporting offshore wind turbines. So a little bit about the technology. SATH takes the name of Swing Around Twin Hull and is a floating wind platform, which is basically grounded on three aspects. So first, the use of concrete as main material, then its unique platform configuration, and finally, the single point mooring. So why use concrete? So concrete, when compared to steel, has a lower carbon footprint, so that's the first benefit. And it also has a lower construction and maintenance cost. Then it helps to enable the local content in a project, and this is valuable when you want to reduce the associated risk of importing the raw material. And in terms of structural performance, concrete has a better fatigue behavior, which can lead to an extended lifetime of the structure. So the floaters are two cylinders in parallel with a circular cross-section. So this cylindrical shape allows a big reduction on the wall thickness, which also means a decrease on the weight and on the draft of the whole platform. So at their ends, we have the conical shells to achieve a better hydrodynamic shape, which reduces the wave drift forces and the drag coefficient. So then the floaters are connected one another by these three transversal frames that you can see on the figure. And well, in the upper picture, you can see a longitudinal cross-section, which shows the transverse bulkheads that stiffen the section and also divide the floater in watertight chambers, which provide stability in damage conditions. And at the lower part of the platform, we have the heave plate. So the purpose of this heave plate is to increase the hydrodynamic water added mass and also the viscous damping. So what it does, it moves the natural oscillation periods of pitch and roll outside of the wave period range, and it also overdamps the heave oscillation motion, avoiding amplifications. And finally, we have the transition piece, which is the connection element between the platform and the tower that supports the turbine. So well, its design is quite project specific. And then we have the single point mooring, which is the mooring system chosen for the SATH technology. So then it's a proven and used concept that comes from the oil and gas industry. And while this system, how it works is it allows the platform to freely rotate around a single point as a weather vane. So at the end, it helps to reduce the environmental forces on the platform. And also it helps the yaw control of the turbine to orient the plane of the rotor perpendicular to the wind. So in that way, in the last figure, we can see that the axis of the SATH platform is located at the stern, so that the vessel approach can be made from leeward with the same equilibrium orientation with respect to the wind. So DemoSATH is a pilot project in which RWE, Kansai Electric Power, and Saitec Offshore have deployed a floating offshore wind turbine in the coast of the Basque Country. So the prototype is equipped with a 2 megawatt turbine, which has a rotor diameter of 82 meters. And the platform has a length of 64 meters and a beam of 30 meters. And well, the platform was constructed and assembled in Bilbao's harbor. And in September of 2023, it was installed 2 nautical miles from the coast in BIMEP, which BIMEP is an experimental offshore platform. And well, the depth in that area is around 85 meters. So DemoSATH, the milestone is that it represents the first floating wind turbine of the Iberian Peninsula connected to the Spanish grid. And well, a significant point in the project is that the 75% of the construction budget was expended on local suppliers. So inside a perimeter of 25 kilometers from Bilbao's harbor. And well, here I have a short 2-minute video to have you to get a little bit an overview of the project. So let's see if it opens YouTube. Yeah. So, yep, hope you enjoyed it. And well, if anybody is curious about the project and fancies to learn a little bit more, there is a documentary produced by Discovery Max, which shows a more detailed explanation of the construction and installation process of the DemoSATH. So you can find it on YouTube, in Saitec Offshore channel, or if you search megastructures in the sea, the searcher, it will appear. So regarding on in what are we working now? So Saitec is self-promoting 2 floating offshore pre-commercial wind farms in Spain, with the main objective of demonstrate the SATH technology on a full scale. So first we have Medfloat, which will be located at more than 15 kilometers of the Bay of Roses in Catalonia. And then we have Geroa, which is defined at 10 kilometers of the Basque Country coast, so close to where the DemoSATH is now. And well, both parks will use 50 megawatt turbines and will have a maximum total capacity of 50 megawatts. So, well, in order to put numbers to that jam, if in DemoSATH we were talking about 82 meters of rotor diameter, here we're talking about diameters between 240 to 260 meters. So the change is quite significant. Okay, so, well, now that I've briefly presented SATH Technology and the DemoSATH project, let's move to the specific topic of today's webinar, which is to talk about the role that Rhino plays in the design process of Saitec Offshore. But let me start by answering first this. So why, back in 2014, Saitec Offshore decided to use Rhino as the main 3D modeling software? So first was the user-friendly interface. So Rhino is very accessible to beginners, as it's quite an easy-to-learn software. And this was an important asset, as in 2014, the technology was only an idea, and Saitec Offshore didn't have a big expert modeling team. So that was the first benefit. So then the versatility. Rhino is a perfect software when creating complex 3D models and difficult geometries, which is kind of our case. And then we have the parametric modeling. As the design process is an iterative process, it was a requirement for the software to allow the parametric modeling. And then the different rendering options and plugins that Rhino offers was also an additional advantage of the software, as it highly improved the staging and the visualization for commercial purposes, but also for the internal communication. And finally, the compatibility. So the compatibility with other software was also an interesting point in order, for example, to produce the construction drawings for the DemoSATH project or other projects. So this is the design workflow of Saitec Offshore, which at the end it comes to an interactive process among the 4 departments. So today we're only going to focus on this first part, so as it's the one that involves the use of Rhino. So looking at this workflow, it can seem that this path is only run once, but well, it's important to highlight again that this is an iterative process. So therefore we come back at the first point many times, and this is why we needed to develop a parametric design. So what do we do when we start a project? So first we receive a number of inputs from the project. So regarding the wind turbine, we have the rotor diameter, have the minimum clearance from blade tip to MSL. So it's the lower point of the blade to the mean sea level. So it's this distance that we have to assess. Then the rotor nacelle assembly weight and its center of gravity. And then we have also the preliminary design of the tower. And then we also have information about the electrical components. And finally, we define the density and the dimensions for each element. And with that, we have our preliminary design, which is usually based on our experience with previous projects. And this is how it looks model in Rhino interface. So this is a simplified model. So first iteration, we would say, and with different layers described on the side. So once we have the model, we start the post-processing, which we do it using RhinoScript. So what we basically do is we call a text file where the layers that we want to include are defined together with the associated densities. You can find it here. And the script extracts the physical properties of our interest in another text file, one for each layer. And you can see it here. So, well, I guess you're wondering why the file is full of X. So due to confidentiality reasons, we can't show you real values and results of our models. So I will describe the procedure and show you the different tools we have, but I won't present any real value from our calculations. And then using a script developed in Python interface, we obtain the global characteristics of the whole platform. And then we get the mass model, which mass model is what we need to send to the hydrodynamics team. So the mass model is composed by two files. So the mass model summary, which gathers the information of we need in order to do the stability and frequency domain calculations. So as you can see, it includes the total mass, the center of gravity, and the radius of gyration for each axis. Then also the hub height and of the turbine, and a reference distance to the tower base. This is internal things. And then we have the properties breakdown, which at the end is a file that disaggregates the different properties of every layer. So we mainly use it for double checking and to make sure that everything is right. But apart from the mass model that we need to send to the hydrodynamics department, we also need two things. So first, the panel model. So the panel model is the external geometry of the floater and the plate. And then we have a text file where all the Morrison elements are defined. So we're not going to enter on what is a Morrison element, but basically they are the slender elements of the platform, such as beams or columns, which are submerged. And these two files are imported to Jenny, which is the interface that meshes the bodies. And then the combination is incorporated to HydroD, which carries out the hydrodynamic calculations. And well, I prepared a short demo in order to show you the process I just explained. So this is a simplified folder structure that we follow, which inside 3DM we access to the different models. So to give you an idea, only in DemoSATH Project we work with 3 different models. So these start having more than 40 versions, yeah. And in the definitive version, we operated with almost 30 iterations. So here we're talking about model 3, version 42. So the model I'll show you now is the as-built model that we calibrated once the platform was constructed and installed. So, well, you can see that it contains all the construction details. And on the side, you can see the different layers that are defined in the model. So as it's an as-built, we have quite a lot. So for example, we can go to the heave plate and select it. It selects all the heave plate that we have on the platform, and then we also can select the horizontal ring of the transition piece. So this is how it's integrated in Rhino. And then if we now access to the RhinoScript interface, we have here the script that I mentioned before. So what it does first, it calls a text file called layers underscore the iteration number. So in our case is as built. So these are if we go to the file, these are the different layers that we want to extract information. So usually here we have the sum densities for reinforced concrete, primary steel, or also adjusted densities for the known weights, such as the turbine or the electrical equipment. But in this case, as is as-built, we adjusted the densities with measurements obtained in the tests carried out during the construction. And what the script does is to select these objects for each layer and extract the physical properties that are of our interest. So for example, we have the surface area, the volume, the center of each element, and the inertias. and then we use the append command. Use the append command to put them on a list. And to obtain the inertias is like using the volume moments command in the Rhino interface and extract the ones that we want. So for example, if we select this random element, so we can see the different inertia values that Rhino provides. So if we come back to the script, the next step is to save all this information in text files, one for each layer, inside the folder that we have with the same iteration name that we described on the top of the script. So here we have the different layers together. So there's all that we selected in the pass file. So in this case, if we select one, we can see that we've stored the surface and the volume, the center of gravity, and the inertias reference to the center of gravity of each element. But as I said, we could also extract the radius of gyration, the inertias on the origin of coordinates, and other parameters. And then we move to the script developed in Python. So what we do here is we first define the work paths for the inputs and the outputs. So from where we extract the information and where we're going to save it. Then we read the layers file and the corresponding densities. So for each layer that has more than one closed polysurface, for example, imagine the plate has different polysurface in the layer. So we calculate the physical properties of the whole element, and then we apply the densities to obtain the total mass for each layer. And we calculate the global center of gravity and the inertias. And lastly, the radius of gyration, which is what the hydrodynamics department needs for their calculations. So then we put together different results in the format that is convenient for us, and we save it. And here, well, this is a list of the different iterations and the case where we define the hoop height. So if now we go to the folder where we save the inputs for the hydrodynamic department, we find 3 folders. So in the hydrod library, we save 2 things. So we save the mass model and the breakdown. So as I said, the mass model contains a total mass, center of gravity, and radius of gyration. So again, with the X. And at the end, what is important to notice is that to a hydrodynamics department, we only giving them 1 point. So it's in the center of gravity. And then we have the properties breakdown, which contains the information for each layer. So in case we need to double check or analyze element by element. So the last thing that we need is the external geometry. So if we come back to the model and select the specific layers. So here is height model, which at the end are the floater and the plate. So we only export half of them, as in Jenny, we are able to apply this symmetry to then have all the platform. So worth to mention that here we really don't need volumes, as we're only interested in the shape of the body. So there's no need to have a closed polysurface for the volume. And this step is maybe the most sensible, as depending on how it's modeled in Rhino, then in Jenny we sometimes we have some tolerance problems. But yeah, so we select them, we export them, and we need to save as is file, which is the point SAT. So after saving that, we can go to the folder in order to check if it's the right iteration and the right model that we then gonna call in the hydrodynamics calculations. And then if we go to the geometry lines folder, we have the bin files, which contain the Morrison elements. So inside them, we define the section of the element, diameter or sides, depending on the type of the section, and also in the initials and endpoints. And well, we also include a graphical visualization of the elements. And in this last folder that I'm going to show you is the hydro results, where we store the results coming from the hydrodynamics calculation, which makes us to take a decision whether if we are happy with the results or not. But well, this I'm going to enter a little bit more deeply in the section 5. So, yeah. So, well, the good thing of having a centralized model is that Rhino is like in Rhino, we also can export information to other software. For example, for the tower design that I'm showing you now, we extract some values from the model, which are required to study the frequencies of the tower. So they have the transition piece and the tower they model in their software, but we give them the information as a mass model for their calculations. That then it's gonna they're gonna affect tower section. So at the end, again, it's a kind of iteration process. And also for the domain, for the time domain analysis and the mooring system design, so we can make use of the information we take from the 3D model. And well, let's move to the parametric design. So I would like to come back to the workflow scheme I showed you before in the initial of the first section, of the fourth section. So what we've seen until now is the first pre-designed part, so the first iteration. But as I said, in HydroD, we obtained some results from a stability and frequency analysis. For instance, the natural periods of the platform, or the draft, or the stability safety factors. And imagine that, for example, we see that the platform lacks from floatability due to the new turbine weight. So a decision could be to change the geometry in order to gain floatability. So then we came back to the same point in Rhino and we review the process. And this can go over and over again until we think that the results are appropriate. But then we have to move to coupled analysis. So with transfer functions and other outcomes from HydroD, we go to the time analysis with SIMA. We use SIMA. So in SIMA, we model the tower and the turbine, the mooring system, and we also calibrate it with past experiments. And then we obtain the motions and the loads in the time domain. So here we need to come back to the initial point as the mooring system is well designed and we have a new weight. So we need to update the new results and also pass by the hydrodynamics calculations. But well, for this mooring system, it normally doesn't change much as the mooring weight is very similar compared to the platform one. And then we have the results from time analysis. So together with the pressure and the inertial loads transfer functions, we send that to the structural department, which they work with MIDAS software. So for example, here you can come the structural guy and say, okay, I've done the fatigue analysis in the transition piece, and we need to change the section of the legs. Or that because of the hydrodynamic loads in the plate, we need to, for example, increase its thickness. So once again, we need to come back to Rhino and start the process again. So the main idea that I wanted you to capture is that this is an iterative process, and doing all these changes manually in Rhino implies spending a lot of time. So here I gathered up a summary of the design parameters that we usually check. So the first part is what we verify with the first frequency analysis. So for example, periods above 20 seconds, stability, safety factors in intact and damaged conditions. And we also have the strength requirements in the different platform elements and also the natural oscillation periods of the tower. So like summing all this up, so in the early design stages of a project, we have automated the process in order to don't spend a great amount of time modeling manually the platform, and also the modifications required in each iteration. So again, it's only for the early design stages, then the modeling team enters, and we usually do a more detailed model. So here I have the second demo. So yeah, it's only to briefly show you the parametric script. So first we enter Rhino, and then we go again to the RhinoScript interface, and we choose the parametric model which are we interested with. So we have different ones. So at the beginning, we define the work paths for the inputs and the outputs. And the first thing that the script does is to call a text file, which is called inputs underscore model underscore the iteration number. So if we go to this file, we can see all the parameters that we define in our parametric model. Again, these are random values, as we can't show you real design values. But well, to have you an idea, I think it's okay. So on the top, we have the principal ones, which are the ones that we usually change, which first. But if we go down, we define the beam sections, for example, the diameters of the columns, and finally the tower properties and the center of gravity of the turbine. So if we come back to the model and the script, we start by defining the layers that our model will have. So again, a list of these layers. Then we define the cylinders. Then we move to the beams. So usually our common process is to define first the curve, then the surface and extrude, and have this constructing the polysurface. So then we have the cones, the cylinder gantries. We also have the bulkheads, the heave plate then. So then for the heave plate, we define also the nerves of the plate, the connection beams. Again, this is an example. So for example, in other parametric scripts, we don't have, for example, the nerves of the plate. We have another type of structure. Then we have the bow landing structure, also the single point mooring. That usually is the one that it's more difficult to model, as they have a lot of intersection between beams. Then the transition piece. We also have the tower, the layers defined by position, such as the mooring or the turbine. So we don't model the turbines or the mooring system. We put a closed polysurface like basic, and then we put we assess we associate a density, and finally we have the panel model that we export to IRD and the Morrison elements. So if we run the script, we obtain the model platform. So this, for example, is an old model in which what we wanted to have is symmetry with the boat landing structure. So as you can see, it doesn't have a lot of details as it's a pre-design, and we are only interested in the global behavior of the platform. And well, on the side, we have the different layers that we have defined before. So for example, we can select the simple single point mooring, the block, or for example, we can select the boat landing, that here it's symmetric. And what we can do now is to say, okay, for some reasons, we need to change the parameters as the inputs of the project have changed, or okay, we're working in another project. And again, this is a random example. So for instance, we can increase the diameter from 16 to 17.5. Then the separation between cylinders, we can increase from 30 to 38. And then the length of the cylinders from 50 to 65. So this is only a basic example that we don't model. We don't change the other parameters. So we save it, and if we come back to the script, we only need to change the iteration. So in the first line, so now is iteration 2, and we run it again. And well, as you can see in the new model, now we have these larger and more separated cylinders. So, well, this is how we can reduce times in a modeling process in order to find the optimal design of the platform. So instead of changing manually, we can only change these parameters and run the script again. But again, this only for simplified models in the early stages of a project. And well, and only add that what I explained before, that if we have major changes, we need to readjust the script a little. So since some elements are dependable on others, so that's why we have different versions depending on the project that we're working on. And well, that would be all from my side. So I'll stop sharing my screen. So So Mikel can jump in.
Okay, thank you. So now I'm sharing my screen. And I start with my part of the presentation. Okay, hello. I'll be speaking about the modeling process. So in the initial stages, we try to gather ideas and to model it with basic forms and small scale models. So as the model evolves, it gets more complex because we associate different calculations in order to ensure its feasibility. And so it is, as we add more details, it gets more complex and more close to the reality. And in this process of developing, we face different problems. Some of the problems we can see here that we have faced are the mooring and how to anchor our platform to the seabed and how to connect our generator to the grid. So solving these problems adds more details to this model, and now we get to something that is quite near to the reality. It's not constructive, but it's very close to the reality. We have a very detailed version, and we can start thinking about how we will construct it and how we will launch it to the water and how we will transport it to the designated area. And now, yes, we have our final model. In this final model, everything is defined. We have the concrete shapes, all the mechanical and electrical installations, such as the HVAC or the transformer. We have all the mooring lines, and we have checked with this model the feasibility of constructing this, and we have analyzed how to launch it from the dock to the water and how to transport it to the designated area. So here we can see a general overview of our project. We can differentiate for main parts. The first one and the more obvious is the platform. The main objective of the platform is to keep afloat all the platform itself and the tower and the wind turbine. Then we have the tower and the wind turbine. The tower holds the wind turbine and houses all the electrical installations. Now, we have here 6 mooring lines. As I said, these mooring lines help with the stability of the platform and the dynamic and static cable that connects to the grid. We have one that is static. It just lays in the seabed, and this dynamic allows the platform to move. So now we are talking about our 3D model. What we are going to see is an as-built model. That means that we have modeled everything just like in the reality. We have all the concrete forms, all the mechanical and electrical installations. We have all the embedded elements, such as the rails and the metallic structure, all the mooring lines. So now I'm going to speak some of the critical points of this platform. This here is the SPM, single point mooring. So here you can see that all the mooring lines starts in this point. It also is the point of connection to the generator and the grid. And it's the rotational edge of the platform. All the platform turns around this point. Now, what we are seeing is a floater. The floater main objective is to keep the platform floating, of course. It is made out of concrete, but it has inside some bulkheads that stiffen it, and it is accessible from the top, and here you can see a ladder that gives access to a platform inside it. And also we have some mechanical installations inside, like the pumps, just in case we have any filtration of water, we can get out of. So now we are talking about the tower and the TP, transition piece. This transition piece is an intermediate element between the platform and the tower. It stiffens it, and when we talk about the tower, it holds the wind turbine and houses all the electrical and mechanical equipment. Here we can see the HVAC on all the different occupation, and here we have an inner view of the first floor of the tower. In the left side, we can see the transformer and how with ladders we can reach the other floor. And this here is a false floor, and you can reach it from here. So now I'm going to show you our model. Here we can see an overview of it, and so I will show you these elements, and also I would like to show you a more in detail of one of these mooring lines. So here we can see the anchor, and all this part of the mooring line is buried in the sand, and this buoy helps us with this rope because we don't want to hit the ground. So if we get closer to the SPM, we see that again we change our fiber rope to a chain. This is the connection, and we get to the SPM. So we can see the SPM from the exterior, and now we are going to activate these sections to see the inner space of the SPM. So if we activate this, then we can see how it's the inner space. Okay, we access from this place. We come here, we have a ladder to access to this platform and do whatever operation of maintenance it's need. I'm going to show you the other point of view so you can see in a correct way everything. And so now we get closer to it, and you will see all the details about it. As I said, this is the edge, the rotational edge of the platform, and you can see the bearing over here. So now we are moving to the floaters. Let me first deactivate this section. Okay, so now I'm turning off these layers, and you will be able to see the inner spaces of the floater. Okay, 1 second. So yes, now what do we see? This thing in blue are the tendons. As I said before, the floaters are made out of concrete, but are reinforced with tendons in the interior. If we get closer, we can see the reinforcement of the head. And now, yes, turning off these two, and you will be able to see all the interior. Here is the access from the top, and here we have a platform and different ladders to access the lower part. We have pumps in the lower part to get the water out if in any case. These bulkheads are made out of steel and stiffens the the floater, and now we are going to see another critical part of the platform, the tower, and we will see it from this point of view. Okay. Here we can see how to access the first floor. Here's the transformer. We have in the first floor technical flooring and all the cable trays. We are able to see everything, the different electrical installations, all the ladders to the access of the different floors. Now, I will show you the other one. Just give me a second, and I activate this one. And I think it might be of your interest to see from this point of view everything. And here we can see how it is, maybe in a better way. So here you can see everything, how is it, and how we reach the different floors. So now I go back to my presentation and I keep talking about this. Wait a second. Now I'm going to talk about rendering and the importance of doing renders in our project. Well, we have different objectives by doing these renders. One and the main objective is to show the constructive process to our colleagues. While we are doing it, we want to share and make adjustments of what we are thinking to make and how we are thinking to make it. So as we do renders of it, we identify different problems and we can solve it in advance. So we don't waste our money. Another big objective is the marketing and communication. It's a very common objective in our industry. Everybody does this kind of renders to show the client an hypothetical result. And we will talk about the visualization of the inner spaces too, because it is very important for us too. So I've prepared some images of the constructive process. These images are real, and with real I mean this is the way it was constructed. So we start with some pillars that are just for support the structure. I haven't said it yet, but what the piece that we are constructing here is the cone. So we start with these pillars, and we start by putting scaffolding and formwork, then the concrete reinforcement. We pour the concrete, we set the first bulkhead, and we pour concrete again. We continue this process so we can see the different stages of this process until here we can see again another bulkhead until we get to the final piece that is this. You can see here, and it was constructed like that. And also, I'd like to talk about rendering, about marketing and communication, because it's very helpful for us to show people, and they can understand how big is our project. And we relate our project to something they might know. In this case, this is the Athletic Football Club stadium, and people usually know how big is a football field. And related to our project, this football field, people can imagine how big it is and get an idea. And visualization of inner spaces. What kind of objectives do we have by doing this? So one and the main thing is having a comparison with the human scale. When we model or do plans, normally we cannot, we don't have the idea of how big or how small things are. So by putting an operator or a person there, we can imagine how big it is and how easily you will have access to something. And also, it is important for the equipment arrangement, how things will be arranged in an area. And by that, we improve all of our designs. What softwares do we have used? Mainly two, V-Ray and D5. V-Ray is a industry reference software. It's very powerful and gives very detailed renders. And D5, it is very easy to understand and to use. It has an outstanding rendering speed, and you can preview it in real time. So now I'm going to talk about interoperability. We have mainly used Rhino for modeling. We have used AutoCAD to make plans, and we have used Revit just for modeling the concrete reinforcement. And then we have used Navisworks for sharing with our colleagues our models. And here you have a little workflow of our work. We start by modeling the concrete forms in Rhino, and we start a lot. So we share these forms with our colleagues via Navisworks, and if everything is correct, or if it needs an adjustment, we start again this loop until everything is correct. So if everything is correct, we export it to AutoCAD and do the drawings, and at the same time we export it to Revit to make the reinforcement, the concrete reinforcement. So we start a similar loop in which we make several adjustments until everything is correct. We keep sharing with our colleagues via Navisworks, and when we have everything, we do the PDFs. So I would like to help Guillermo for letting us this spot to speak about our project.
Thank you so much. I'm not sure if you want to add something. It was a really nice presentation, and it was really interesting to see the scale of the project and also the details of the model in Rhino. Really nice to see all the details that you have from such a big project, and also how you combine it with other softwares. And I see there are some questions related to that, because the first one is how can you connect a spider to Grasshopper? I'm not sure if Oriol showed that.
Yeah, this, I guess it's mine. So, well, we don't use Grasshopper when modeling in Rhino. So we thought about it, but we decided that we feel more comfortable with Python coding. So what we do is we open the Python programming interface directly from the RhinoScript interface. That's what we do.
Okay, thank you. Yeah, and the second question was about what you saw now, Mikel. Well, sure. Sorry, yeah. Oriol?
No, yeah. Well, the second is the Rhino API, right? In Spider.
Yeah,
So
yeah.
Also for me. So also no. So we make use of the text files to connect both interfaces. So for example, from RhinoScript, we get some outputs in text file, and which then these same text files are the inputs in the Python script.
Okay. Yeah, perfect. Yeah, I was saying the other one that was about how do you go from the 3D model in Rhino to manufacturing drawings, and you were showing how do you do them
Yes.
in AutoCAD?
Yes, we use AutoCAD. We export the images from Rhino to AutoCAD. There is a command in Spanish is dibujo 2D. I think
it's
it's
make 2D.
2D. Okay.
Or in sections, and
Yes.
it's a normal workflow. And yeah, and how do you keep track of all the parts and keep association of to bombs and that you must have to use in the production of the platform?
We normally do this workflow. I mean, we start again and again. I mean, when I saw the workflow, we model and then we do changes and changes. We do plans at the end of this workflow, so it's we are not changing plans all the day, no.
Okay. Yeah, and about the rendering part, Team FAM says that Enscape is also good for render, and you can also use virtual reality to see how big or is a space. So that's also one option. I'm not sure if the D5 render has also virtual reality.
Well, I don't know. I don't know that because we are a big group, a big team, and we have different modelers, and each one has its does different things. And I wasn't doing that, but I think that using virtual reality could be a big thing and really helpful for us. Yes.
Yeah. Another Belal asks, did you use the federated method for modeling the structure?
No. We use just one model, and we integrate everything in that.
Okay. And why you were using Navisworks after Rhino and not connect directly Rhino with Revit?
Well, we use Navisworks just to share with our colleagues what we have. I mean, we don't have every colleague in our company doesn't have a license to open the model. So this is a good way to show our colleagues that are calculating things, what we are doing and the different changes that we have made.
Okay, thank you. Yes. And the next one from Tengui Kokyo asks, did you manage to automatize the mesh generation from the SAT file to FEM file from Hydrodynamics?
Yes. So yeah, we also have a Python script that what it does is to take the.
Yep. Oh.
Oriol? I think Oriol has problems with the audio.
No, we can't hear him. Not sure what happened.
I don't know what is happening. Maybe.
Yeah, maybe he can talk in your computer.
Okay, yeah. Just wait a second.
Yeah.
He's getting another headphones. He's getting closer. Sorry for the inconvenience.
No worries.
Well, sorry about that. That just the screen went down.
Okay.
So yeah, what I was saying is that we have a Python script that it's automatized for taking the inputs that the outputs that we have from the RhinoScript and the mass model, and it goes to Jenny to create the mesh, and then it's imported directly to Hydro-D, and then we receive a text file with the results of the stability and the frequency domain calculations.
Okay, perfect. Thank you. And the next one is also similar. That is, could you explain why RhinoScript was chosen over Grasshopper with Python?
Well, basically, it was because we had like a quite good know-how about modeling with Python interface. So as our platform is quite, the geometry is quite not singular, let's say. We're trying with the Grasshopper, it had a lot of variables and a lot of different well, difficulties. So what we did is to have all the parameters in this text file and code by with Python to construct the geometry.
Okay, perfect. So I think that's all. Well, thank you again. A lot of comments saying excellent presentation. Thank you.
Okay, it's a thing, Mikel. Also, so sorry about that last problem. So thank you for having us here, and yeah.
Thank you for the presentation. As I said before, I will try to upload the presentation tomorrow to YouTube if you want to check it again.
Okay.
If you have any more comments, you can send us an email or type the comments in the YouTube recording. So thank you, Mika and Oriola, and to all the team for the presentation, and thanks for showing this great project. It was really nice. Thank you so much.
Thank you.
Have a nice day.
Okay.
Bye. Yeah.